two branches that are in parallel ultimately have the same climb. They all start at point A, do a bunch of stuff to get to point B, they make the same climb. Now we'll see more complex circuits where the speed of the climb might be different, but it's always the same end result.
We're just all over the place today, Chris.
Sorry, nowhere near you.
You're right, you're not. I'm so far superior.
So looking back at project 4 again,
Chuck will do it in the same.
since bulb 1 and I think M1 we called it, are in parallel with each other, they're each independent branch. So bulb 1 should be just as bright as it was back in project 1. The fan should be just as fast as it was back in project 2. And they should be faster brighter than project 3 because now it's a parallel branch, the resistance is going to be less and nothing's going to be slowing down the charge. And last question says, I pull off this connector, what's going to happen? And that should destroy the circuit because there's no more continuous conducting path. No, there's no reason for that. Go back over here. Thanks.
Oh my God.
You have markings.
Because you're on time, too.
Okay,
You had so much noise.
project 4 questions, and you're still talking about it. So at one picture now, we have project 1, 2, and 3. We're going to build project 4 over here. Again, we'll note back in project 2, the fan's faster than project 3 because there's more resistance in the series. Those two things. So there's a light bulb, here comes our fan.
No, you're gonna use the cool.
Well, I can't change it now.
Oh.
You gotta do really good the thing.
I had to rotate it properly.
Now, is this actually you controlling the hand before? And then
Yeah,
you decide
I
to-
just recorded my screen.
He's thinking.
Yeah, we discussed this a while ago, but
Yeah.
You weren't here for that.
There's a master plan to do this.
What?
Awesome. Yeah.
So here come the lines.
A computer.
Here come the wires.
Oh, get it? He's controlling.
you can I think at an angle if you want.
I believe so.
Circuit, Travis.
Now we're going to turn the switch on. You can see that the fan here is the same speed as the fan in project 2 as predicted, and the light bulb is the same brightness as project 1. We'll put some current meters on here, I think. Yeah. So we're going to measure the current across, the current into the battery is 1.2 amps. And so let's see what the current in each branch is.
This is a really nice program to manipulate.
So the current through the light bulb appears to be 0 right now. That's not working right. I think it's an okay program. It's the best free one out there. What are you going to do?
5-1.
I'm not going to do that. That blue one's not working yet. Let's see if I fixed it. I think I fixed it. I'm thinking right now. There we go.
Oh.
So each branch is approximately 0.6 amps, and the total is 1.2 amps going back to the battery. That's what we predicted from before.
That's good.
Thank you.
No, it's not.
So speaking of that, current in parallel, we know that in parallel the current should add together. So the current across each branch should add up to the total current coming out of the battery. That's pretty simple.
Your current isn't volt, current is ohms.
Current is amps.
Amps.
Ohms is resistance. Think about it, if you're facing a lot of resistance in life, you want to meditate, you feel like ohm. That's your ohm is resistance.
Resistance.
That's what I think of when I
I
think
like
of that.
that.
Project 5. Took the fan. How is project 5 different than project 2?
It's 2 batteries.
No.
In no way is it different than Project 2.
What's that? The fan is flipped 180 degrees. Now the electrons are entering what we label the positive end and going out the negative end. What difference did that cause to happen?
It reverses the direction of the fan.
Good. So some devices, if you send the current through it, quote unquote, backwards, it's going to make the device run backwards. Not all devices, some devices will break if you do this. That's why some, especially nowadays, devices have what we refer to as polarized plugs, so that you can only plug it into an outlet a certain way, so you can't cause this to happen. But then we flip the fan, and that causes the air to blow down instead of up, so you stop it, flies up in the air.
Oh my gosh, look at all those movies. Do you ever pick the sweetest thing?
No, I use the fan every time
Choose the 9-volt.
for consistency.
9E.
The 9-volt breaks the light bulb sometimes.
Here we go. You're so close. Wow.
We'll skip ahead a little bit. On the top one, that's like project 2. The current runs the fan one direction, and this one down here now, I flip the fan over so the positive end is touching the other side of the fan. Hopefully the fan will spin backwards. And see the fan there spinning different directions. The fan won't fly anywhere.
How come you're all tabs screen on this so different?
Can I do this on my home computer?
Yeah, but do you have Facebook?
No, it's just some stupid add-in thing. Project 6, now we have the fan and the light bulb put together. What's different
There.
between the last project we just looked at?
And a lamp.
Resistance.
You're good. Light bulb or resistance, everything's the same, but it goes
Get
slower.
home.
And that's why you should have noticed that this fan didn't really fly up in the air because it was moving slower. It's still blowing the same way, but it didn't really go up. Well, one way's up, one way makes it go down. I don't know which is which. I mean, you can call up or down, whatever you want. Project 7 was kind of the big one there. So we now have a battery pack coming out to a switch and a bulb and then going up to a fan. At the beginning, what does, or where does the charge flow through this circuit at the beginning? Before we push the switch. Goes up to the lamp, to the fan, back to the battery pack. So it's very similar to project 6, I think, or project 3, where we have a bulb and a fan in series, and so they're going to be a little bit slower. When I pressed S2, what would happen?
It becomes parallel.
So the lamp got dimmer, fan got faster. Why? Now these are in parallel. What's that mean? Or why? There's less resistance where? Good, the switch is less resistive than the light bulb once you complete the circuit there. So the vast majority, like 99% of the current, is going to travel through the switch because it's a much easier path. It's kind of like walking a mountain. You can either climb over a huge boulder blocking a path or walk up a nice escalator path. You know, which one are you going to pick? Most of us are going to pick this path. There's always some crazy kid who wants to climb over the boulder and try and kill himself that's going to go up that harder path, but just because that's what people do. But for the most part, we're going to all take the simpler path. Up and around. What is the potential, or how does the potential between this spot and that spot compare with these two spots? Should be the same potential difference because we're taking the same, we're going across the same climb there. This one's going to be substantially faster, but you're each going to gain the same potential by the time you're done. So let's see if I wrote anything interesting. Fan speeds up. S2 is essentially a bare wire with very little resistance. Most of the current goes up S2. Okay, so let's watch a movie. I think this is the good one. Now we got our circuit kind of built here. Steve, all fast, stop talking.
I'm sorry.
Just face forward, it'll be easy. If you want
That
to
doesn't look the same. Yeah, why is it a
Oh.
resistor?
I added a resistor because the program, if I don't, it doesn't send any current this way. So it's being a little too literal, so I have to, so it treats the wires as resistanceless. So I have to add that just to take the program out. Good
Wait,
question.
no, quick question though. Why is the...
Okay.
It's a terrible question.